techniques that we haven't learned. One of them is simple partial fractions. Basically what you're doing with these different techniques is addressing specific situations that occur with functions that have their own unique solution system, right? So just to kind of jog your memory, evaluate this integral. Right? Yeah, you're going to use that today. Okay. So that you already know. This is a rational function, right? That we can integrate with natural logs. Okay. What we're going to run into now is something of this nature. Okay. Which we cannot integrate with the current knowledge, right? This is not a natural log integral. But what we're going to do is we're going to move it into, we're going to create two fractions that look like this. And it's going to end up with an answer like this one.
So you just factor that?
Yeah, so we're going to factor this, we're going to split them apart. And that's what partial fractions are. We split the two apart, figure out what the tops are, and then we integrate with the split apart version. Okay, so it's not really hard, you just have to learn the pre-calculus behind it. That's all today is the pre-calculus lesson for you, right? So let's take a look at that one on a new slide. All right, so we need to break this into its factors, which are right. That so this is where we create our partial fractions. And again, just pre-calculus. We want to break these apart into some two fractions, and we can integrate these out the backside, right? We just need to figure out what A and B are. Okay, and then we can split apart and we can do our calculus. Okay, so do you remember how to solve rational functions? It's actually pretty easy. To eliminate the denominator, what do I need here for a common denominator? X plus 3, right? And I need X plus 2 here. Right, so that's what I'm going to do, is create my common denominator. And now the denominator can go away. So all I have left is 1 equals A x plus 3, B times x plus 2. No, and this is as far as it goes in Calc BC, is simple partial fractions. Right, these can get really nasty, if we wanted to. If you look in your book, the second half of this section is all the really nasty partial fractions. We just stay simple, linear, non-repeating even. We don't even repeat factors. Okay, so we stay in this arena. Okay, because we know that this works for all real numbers. Okay, so this is defined for all real numbers. We can choose x values to solve this problem. Okay, so what x value would I choose here to make that 0? -3, right? So we're going to set x equal to -3. Plug it in. and solve for b. Because now a is now 0, right? 0 times a. So this is eliminated. So we have 1 equals negative 1b. So b is negative 1, right? All right, so now we have our b value. Following?
So then you set the next one equal to -2.
Right. Yeah, same. So we get 1 equals a times -2 plus 3. B, of course, is going to, that's going to disappear. So a equals 1. Right? So that's the pre-calculus. Just figuring out a and b. Sometimes you'd have an a and b and a c. I'll go through one of those with you. But, all right, so what is our there's our original. Now we can split it up. One thing to caution you about is make sure that you put the letters in the right spot. Some people mix those up when they're trying to go really fast. Okay, so we have a over x plus 2, right? The reason people mix them up is because they look at this one. For some reason, they put x plus 3 with a, but you need to reference the original. And then plus the integral of b over x plus 3. Bless you. Those you can handle, right? Okay. Equivalent statements right there. You've just broken down something we cannot integrate into partial fractions, but we can.
And then you just do natural log of x plus 2.
Natural log absolute value x plus 2. That's going to be negative.
It looks like we could do a shortcut to this. Is there one?
You can get really fast at it by doing a lot of it in your head, because it is usually small numbers that are easily thought out, but
So do we even have to evaluate them?
I would caution you on that, because people tend to make mistakes, just silly little addition or subtraction, multiplication errors when you try to do a lot of this in your head.
Yeah, that would be me.
That would be me. I write all these out. Now, if you can do it without that, I've had students in the past that could bust these out faster than me. Like, we had a competition, like tomorrow we're going to do a little competition, and I had students that will beat me day 2. Right? And I've been doing this for 15 years, so like, just because they're on it and they get it right in their heads. Okay. Are you talking about definite integrals, Kate?
Yeah, so for this, we don't even have to evaluate it right now?
No, right now it's an indefinite integral. Yeah.
Are we gonna do that, where we have to evaluate it?
No, we don't put that on your plate.
Gotcha.
Yeah.
What does that look like, though? Do you have to like mess with the?
Well, all you would have is definite integral. You know, you'd have integrand limits that would stay the same. They wouldn't change, and you'd just at the end here you'd evaluate this just like we would a normal integral. Yeah, it wouldn't change anything, but yeah, don't worry about it. All right, let's look at one with an A and B.
Wait, does it matter which things the denominators are?
Which what?
So does it matter if we put the x plus 2 under the -1?
Yeah, if you switch these, that's what I was saying. If you switch put this here, it's going to change your answer.
But why isn't the x plus 2 with the b?
Is your original setup had the A with the x plus 2, right? And your B with the x plus 3.
So in your original
This is
setup-
where I see a lot of the errors when people do it in their head, because they end up switching them. When they do the integral, they accidentally use this statement when you need to use these together as is. Yeah.
Can your A and B
You can put whatever letter on top you want. I don't care. That's just convention, and that's how your book does it. You know, the next one will use A, B, and C. You could do C, B, and A. I don't care. As long as you put the right stuff where it belongs at the end. Right? Okay. All right. Let's try one that has some junk on top.
Does that say x4 or x plus 2?
X squared plus 2.
On the bottom.
X minus 1, 2x minus 8, x plus 2. Okay. You don't have to write this if you don't want to, but it, again, it keeps my mind on the right track. I set them equal to each other when I write them out so that I see the denominator and the denominator, but it's up to you guys. I would encourage you to do it. Okay, there's our broken down version. All right, so the top has to equal, what is my A gonna have with it here? These other two, right? Yeah, so 2x minus 8, x plus 2. Right, and then B will have x minus 1 and x plus 2. And C will have these two with it. A little tedium, not hard, just a little bit of tedium. The nice thing is when you set x equal to something, it's always in two factors, so it's always going to eliminate two of them. And what you're going to end up with is just one at a time to solve, right? So take your pick. X equals 1. That means we have 3 over here, correct? Yeah, just plug x in. And then, what does that give us? Negative 6 times 3, negative 18. Right? And then that's eliminated, and that's eliminated. Boom. Yeah.
So it's really not that much difference.
No, it's the same problem as before. It's just there's just more addition, subtraction, and multiplication. What's our next x value? Negative 2. Okay. 6, I believe. Okay, that's eliminated. That's eliminated. What do we get? That'd be negative 3, and that would be negative 12. Correct me if I'm wrong. 36. So C is 1/6. You agree? Okay, Canyon, what's the last x value?
Hold on, not quite caught up.
Okay. Thought thought you were. Two separate problems.
Are you looking B right now?
Yeah, we need to figure B out. So we need to eliminate that factor, right? We've done x plus 2, we've done x minus 1, we need to
Just figure out what, you're all right.
4, yep. So 18. And then that's eliminated. 3 times 6 is 18. And then that other's eliminated, so B is 1. Yeah, lots of extended page problems here. So. Just for formality's sake, I'm writing that out. You do not have to. Okay, now I'm going to go back to the original part and place my numbers correctly. So I have A, and in reality you can actually do this. Put it out front if you want, or you can put it here. And then B is 1. And C is 1/6.
So you could rewrite it as, like the first one as -1 over 6x minus 6.
You could. I wouldn't go there. Keep it simple. It's going to end up with the same answer, but yeah, so we end up with -1/6 natural log x minus 1. That's why we keep it out. This makes it easier, right? This one's not complete quite yet. What do I have to put here? We've got a chain rule problem.
Oh, so you just have to do it.
Yeah, 1/2 actually. Remember, it's divide by the derivative? Because if you derive this right here, you get 1 over 2x minus 8 times 2. So we need to counteract that times 2. And then this one is just going to end up the same. Like that. Okay. Yeah. Long problems, just they're not real difficult, they're just long. So stay organized. Okay. Any questions? What's the derivative of natural log 2x minus 8? It's 1 over 2x minus 8 times 2, right? There's no 2 up here. So we have to counteract that with a 1/2. All right, if you're interested, there's an example with long division at first to make things look pretty, and there's repeated linear factors where you'd have like x minus 1 and x minus 1. You could also look at quadratic factors like x squared plus 1 and x squared plus 2 in the bottom.
Is any of that gonna be relevant
No.
to this?
All that we're looking at is simple we'll score this tomorrow. So you get some practice in, and then tomorrow we'll do some more practice over the weekend, a couple free responses. And then should be a pretty low-key week next week. All right, this time's yours. If you have any issues,